Take-home quiz number 2, version 2. I went through this with you guys last class, a very similar quiz. I'm just going to blaze through the answers. So number 1, you should have got 20.0 meters per second at 38 degrees north of east, or you could also be 90 minus 38 is 52 degrees east of north. It all depends on how you draw the triangle, but most of you probably drew it this way. If you didn't get that, that's how I would give out the part marks. Question number 2, very, very similar to question number 2 on your last quiz. I just changed the mass. When you, there's a collision, that's a job for momentum. There's a nice straight line. I can just cross multiply instead of bringing in the heavy trig. And you get 2.36 meters per second. When you now go to energies, you recognize that the kinetic energy final is 0. Your initial potential is 0. And you find that it will go to a height of 0.284 meters, about 28 centimeters, about that high. Suppose the pendulum only reaches a height of 0.15 meters. How many joules of energy? 3.18. That's a bonus 1 mark. That one's all or nothing because it's a bonus. Turn the page. A 100 kilogram shell explodes, boom, into 3 fragments. Yeah, there you go. Anyways, this one was a little nicer. You have mass A, mass B, mass C, and because the initial momentum was 0, your final momentum is 0. Mass A has a momentum of 1280, and it's 30 degrees north of east. Mass B, due north, which was kind of nice, plus mass C. Now, I may have drawn my triangle different from you. I'm not sure. I always had trouble drawing vector triangles. I fake it with you guys, and I've done it for so long now, I'm pretty good. But when I was in high school and in university, whenever they gave me a vector triangle, because I struggled so much drawing them, I always drew the easiest line first. In fact, you may have heard me in my teaching style. You'll often hear me say, get the obvious one, or write something down. So I always draw, since this was the easiest one to draw, I drew it first. Then I added tip to tail, and I knew I had to come back to where I started from. There was my mass C. You might have drawn the 1280 and then the 1200, and I'll show you how that looks in just a second. I did I had to find some angles. This is 120 degrees as it turns out, because that's a 90-degree angle right there and a 30-degree angle on top of it. Gave me 120 degrees. I ended up with a velocity of 61.4 meters per second, and I got 60 degrees south of west. If you drew the triangle the other way, you probably got 30 degrees west of south, which is also just fine. Yep. Yep. Yeah. Usually with degrees, I go to the nearest degree because that is 2 sig figs. And also, 1 degree is about like that big. 1/10 of a degree, I'm not even sure if our eyes can spot that. Probably, but barely. So, yeah. Yo.
You know how there's 30 degrees there? Why is it 60 and a half? Like when you figure out the sign.
Great question. Can I come back to that? Well, you know what? Let's do it, Mr. Duke. Dunk. So I found that this angle right here was 30 degrees. Now the problem is both of these lines are not vertical or horizontal. They're not a north or a south or an east or a west. So I did this. This angle is also 30 degrees because that angle there is also 30 degrees. So that whole angle is 60. And that's how I got the south of west. Start out going west, go south of west to get there. Okay? Or you could have found let me think here, Mr. Duick. 60 degrees south of west is the same as 30 degrees west of south. I think this also ends up being 30 degrees right here if you draw it a different way. But regardless, excuse me. No, that's not right, Mr. Duick. It doesn't end up being 30 degrees. I'm rethinking this. Anyways, that's where I got the 30 from. Is that okay? Yeah? Yo.
Would it make sense to like draw a straight line and then if you do like this angle thing, where like one side be 30 and one side be 90?
Did you draw the same triangle as me, or did you draw the 1280 first?
I did the 1280.
Okay, let me draw that, because part of the reason we're having a tough time visualizing is I drew a different triangle from you guys. So you went 1280 and 1000 like that?
Yeah.
1,200 and 1,000. Good gosh, Duke. 1,280 and 1,200. 1,000 was the other. And coming back to where we started from. So if you drew this, then you just have to find that angle right there because that is next to a nice vertical line. So my method made the triangle easier to draw, but it made the angle tougher to find. I may redo this answer key now that I think about it. Did I answer your question with my drawing? Or were you wondering how to get this guy right here?
Well, because I got that, but then how I got the top angle, so I did 90 plus 30 equals 120, and then it comes out here a straight line.
You did that?
No.
Oh, no, you said
From the top.
from the top? You did that?
Yeah, and then that would be 30.
What would be 30? This?
Yeah.
I think this would be 30. This turns out to be 30, but I think it turns out to be 30 because of a fluke, or does it? No, you're saying, hey, Mr. Dewick, that right there is 30 degrees, and so I have a Z right there, 30 degrees. Yeah, okay, I'm good with that.
Okay.
Yeah, I'd think about that for a while. Good question. Last one. This one turned out actually easier because I gave you both angles, which is why I just asked for the magnitude. There's a collision, momentum before the collision, what's moving? Mass 1. After the collision, both separate. Mass 1, I wasn't sure which way it was coming in. Oh no, it says due east, so I drew that. Mass 1 afterwards has the momentum of 25.92, 38 degrees north of east plus. Mass 2, oh, they gave me the angle. That was really nice of them. 48 degrees south of east, 22.14. So when I add these two together, tip to tail, the nice thing was that allowed me to get this whole angle right away. I didn't actually need you to get a direction because it's due east. That angle, that's 25.92. This angle was 48. Z angles, Z angles, that's 48. And that gave me the 94. And then I used the cosine law, divide by m to get the velocity, 11.92. Is that all right? So there's going to be a tutorial today after school. This quiz is out of 16, not 12. You can get 17. I don't actually want the quiz. I want you to hang on to a study from. So let's do the old person on the end of each row can tear out a piece of paper, write their name and their score on it, and then just pass it inwards slowly. So continuing from lesson 2, horizontal circles, we left off right here. One method of generating artificial gravity in outer space would be to build a circular space station and spin it. We can do that. If we do space travel, fake gravity is not really that big a technological challenge to overcome. If you spin something, you'll feel a centripetal force, you'll feel a fake gravity. Real issue with space travel, like spending years out there, if we suddenly found that 30 years from now we were positive an asteroid was going to hit the Earth and wipe us out. Okay, the world, we could unite, we could build a large structure, we could build a structure that had artificial gravity. The big issue that we have no technology to deal with is the radiation, the cosmic radiation. Our Earth protects us from most of it because of its atmosphere and its magnetic fields. That we can't recreate at this stage yet in our technological careers. And I've mentioned to you the people that are in the space station, the astronauts that do lots of space orbits, they are dealing with health issues. The risk of cancer goes way up. Anyhow, gravity though, not that big an issue. It says this: if this space station has a radius of 5.2 meters, I made this question up and then I went, yeesh, let's make it a real space station. How about 52 meters? Let's make the space station about the diameter of a football field. So instead of 5.2, 52. What does the period of rotation need to be for an astronaut to experience 80% of the Earth's gravitational field? This is a job for a free body diagram. Let's see if we can list the forces on this person. So here's my person, side view and top view. There's the person. What are the forces acting on this person? Now normally I'd say get the obvious one. Why can't I say get the obvious one this time? Why can't what is the obvious one normally been? Gravity. Why can't I say get the obvious one? Okay, we're in outer space, so Get the obvious, the obvious one isn't there. Now, this person is tracing out a circle. That means there must be a net force pointing towards the center of the circle. There must be a force that way. I'm not going to label it FC because that doesn't appear in my free body diagram. And here's my question. What force is that? Friction is a good guess. It's not. You know what? Let me make it a little more obvious for you. Let me see if I can change your relative thinking. Let's make it so that now it looks like the space astronaut is standing on something. See, as soon as I flip it sideways, I always have a bunch of kids blurt out, oh, it's a normal force. Yeah, look, in outer space, up and down and side, left, they're irrelevant. Down is wherever your feet are. Up is wherever your head is. And this person is standing on a floor. It's, as it turns out, a normal force. A normal force. Which makes sense, because haven't I gone on long rants about how what you guys think of as gravity is actually the normal force, the chair pushing back against you, how a good amusement park ride doesn't muck around with gravity. They can't, they muck around with the normal force. So yeah, you know what you feel of as your weight, that's the normal force. So I think what we're saying here is that. Yes? FC is MAC. Which equation for circular acceleration do I want to use? Do I want to use the v squared over r, or do I want to use the 4 pi squared r over t squared? You're right, 4 pi squared r over t squared. Why? Okay. You use the v squared if they're asking for or they tell you the speed. You use the t squared 4 pi if they're asking you or they tell you the period. So it's going to be 4 pi squared r over t squared. That equals the normal force. I don't know the normal force. And I can't quite say, oh, but look, I know another force the same size as the normal force. What I can say is, oh, think. I know another force that's the same magnitude as the normal force based on the word problem. How big do they want the normal force to be? 80% of mg. Oh. Oh! Terry, what do you notice? Mass cancels out. Does that mean if I built a space station, kids and adults could live on it and they would feel the same force of gravity if they were standing side by side? Oh, great. That's helpful. What are we trying to find? Oh, let's get the t by itself. Okay, I think I would move the t squared up here because stuff moves diagonally. And I would move the 0.8 mg down there. And then I'll get the t squared by itself. How to get rid of a squared? Oh, first this looked ugly, but this is actually not too bad. The period that I want this space station to rotate at is going to be 4 pi squared r all over 0.8 g. That's square root of that. Four pi squared. What did I say the radius was? 52 divided by 0.8 times 9.8. Mr. Dewick, why don't you actually write the numbers out? 4 pi squared times 52 divided by 0.8 times 9.8. I went straight to my calculator. And then square root of that, yeah? You get 16.2 seconds. I'd want this space station to rotate every 16.2 seconds. And that would give you probably, you'd feel a little awkward for a few weeks, but your body would adjust, and probably 80% would be enough to deal with most of the other effects of space travel. Your heart muscle would still remain fairly strong. Your bone density would still remain close to normal. That'd be doable. What would happen if I made the radius 4 times bigger? What would the new period be? Can you see it? Jason? Double, yeah. In fact, if you want to double the period, you got to build your radius 4 times bigger. You want to triple the period, you got to build your radius 9 times bigger. So the bigger the radius, the slower the space station needs to rotate, but it's not a 1-to-1, it's a square root, not a squared. We've seen the squared thing before. It's a square root relationship, as it turns out. I guess that would mean that as the radius got smaller, gravity would get less if you kept rotating this with the same period. Now here's what that would mean. B. If you started to climb a ladder that led to the center of the space station, the more you climbed, the easier it would get. Because you would feel lighter and lighter. In fact, in the center of the space station, what would your mass be? 0. Excuse me. In fact, if we were building a space station, probably what we would do is we would have a central, let's put a pen on here. We would probably have a central axis that didn't rotate. That's where the shuttles and spaceships would dock, because trying to dock to something that was spinning would be very, very awkward. And then what you would do, once everything docked, the space shuttle, this would not rotate. You would flip a switch, and now this would slowly start to rotate until it matched the speed of your space station, and now you can climb into your space station quite safely. And in that middle area where you're docking, mass would be fairly small, or sorry, gotta be careful, weight would be fairly small, mass would still be there. It'd be easy to onload and offload stuff. That'd be a good system, actually. If this astronaut climbs, at what radius will he feel 30% of his weight? I think we have the same free body diagram. I think it's still going to be normal force equals Fc. I think this time we want 30% of mg equals m4 pi squared r over t squared. Again, Terry, you're right. Doesn't matter whether he's a kid or a fat person. In fact, I suspect if money was no object, you'd probably set aside some of that central section as a recreation area to go fly. In fact, if really would be very cool would be if you put a pool around maybe the outside, a curving water pool, because it would be able to, because mass, it would be enough mass to keep the pool in there, and you could fly into the pool like Superman, climb a ladder, jump off the diving board. You'd float for a while, but if you were just slightly off center, gradually, you get pulled down into the pool. It'd be cool. Anyways, what are they asking us to find this time? Oh, radius. Let's get the r by itself. I think to do that, move the t squared up, move the 4 pi squared down. Yes? This is going to be 30%, 9.8. Period is going to be, you know what? Your period of rotation is going to be the same no matter where you are in the spaceship. So what did we say it was? 16.2? I'll use the number from my calculator. I think it's still on there, but I'll put 16.2 all over 4 pi squared. Is that right? Ah, curse. I did the same thing last class too. Curse you. Now I got to do this. 0.3 times 9.8 times 16.182 squared divided by, I did the same thing last time. I guess that's maybe a common mistake. I don't know. Forgetting the squareds. Oh yeah, we've done it before. Is it 19.5? Yeah, there, that's a better answer. So artificial gravity, really pretty doable, pretty simply. Back in a second. Oh, a great amusement park ride. The Gravitron. I like this question. I like this question. I like this question. The Gravitron spins its riders around in a circle. If the ride has a radius of 4.8 meters, now there's two types of Gravitrons. There's some that stay level and the floor drops away, and then there's some that go up at an angle, and that's how you appear to resist gravity. How many of you been on the Gravitron before? I am ashamed and embarrassed to say I haven't yet, because it's not part of Playland, it's part of the P&E. And I usually don't go to the P&E in the summer because I always do Playland in May with my physics kids, but I may do it just for that.
When it comes to the Pitt-Meadows place,
they have it here?
yeah.
Right? That's how you should ride it. Right? Let's look at the physics. So, if the ride has a radius of 4.8 meters and it rotates every 2.5 seconds, what's the minimum coefficient of friction required between the riders and the wall of the ride? This looks like a job for a free body diagram. What are the forces acting on this person? Get the obvious one. We are on the Earth now. What else? Let's see if we can reason this. First of all, what path is this person tracing out? So where must my net unbalanced force be pointing towards? Okay, there has to be some force here. I don't know what it is, but I know there's a force there. What? I think it's a normal force. I think it's the wall pushing that person in a circle. This can't be all, though, because if this was all, this person couldn't be in equilibrium. The floor could not drop away. You would fall down with the floor. There must be a force exactly in the opposite direction. What? Yeah. In fact, we've sort of flipped the ground vertically, if you want to think about it, 90 degrees. Okay. So here's our equation. That is equal to centripetal force. And centripetal force is going to be m. Which equation am I going to use for acceleration? V squared over r or 4 pi squared r over t squared? Because you have the period. And by the way, when you go to the Playland and analyze rides, period is the easiest one to calculate. You got a stopwatch, you pick a person, start it, there they are again, and stop it. Pretty easy to find. I don't know the normal force. I can't say normal force is equal to friction. It's not. Any suggestions? Well, sorry? mg plus fm. Are they in the same direction? Then I don't think I want to be, if I'm going to add them, I'd have to add them vectorial. There is a second equation hidden in here. It's a really obvious one that maybe you haven't seen, but I'm going to write it down. Can you see the second equation? A vertical equation. What's the vertical force equation here? That's true as well, yes? I don't quite know where I'm going, but that gave me something else to write down. Wait. There is another way to write friction. Friction is mu times the normal force equals mg. Oh, hey. Could I get the normal force by itself in that equation? How? Cool, this is the first time that we've used friction to find the normal force instead of the other way around. Oh, and I think I can stick that there. And this is nice also because it introduces a mu, which is what the question wanted me to find in the first place. Cool. Apparently, gravity, strangely divided by the coefficient of friction, is equal to m4 pi squared r over t squared. Who's been on this ride before? Did you have to step on a scale before you got on the ride? Why? Turns out they do. What are we trying to find? Oh, cool. I guess I can move mu up there, move all of those down there, and the t squared there. Yeah, because stuff moves diagonally. There's my cross multiplying with a vengeance. By the way, it's for this equation and another even more hideous one similar to this that I showed you that at the beginning of the year that stuff moves diagonally. Because if you could just do this in one step, thank you. There. I think we're going to get this. Mu equals gt squared, Mr. Dewick. Yeah, good point. Divided by 4 pi squared r. Is that right? Let's see. 9.8. I've scrolled down. What did I say the period was? Now, I was making up numbers. Who's been on that ride? Do you rotate once every about 2.5 seconds? No. Faster or slower? I'm going to argue with you guys that I think you're wrong. I think you're getting an adrenaline rush and your judgment of time is pretty poor. I'm going to challenge you guys. Next time, please, if you have any kind of an inner nerd, next time you go on that ride with your stopwatch while you're standing in line, time it, go around once on your phone or on your watch, get that. And then when you're in there, before the ride starts, if you can, quickly pace off from the center to where you're standing in 1 meter steps. Try and figure out the radius, and I will happily crunch the numbers accurately. Let's find out. But I think my time of rotation is actually small. Anyway, 2.5 squared divided by 4 pi squared. And I took a guess with the radius being about 4.8 meters. About 5 meters is really what I was thinking. 5 meters is about from, well, me to Sydney. Is that 5 meters? 1, 2. It's pretty close. Is that about, you guys have been on the ride, I haven't. Is that about how far it is from the center axis to where you are? Or is it closer? Half that? I got to go on this. I got to go on this ride. So you're saying that when they have the little traveling carnival thingy that comes to Pitt, they have it there? When's the last time? When does that usually show up? I don't live in Pitt Meadows. I live out in Maple Ridge. I'll keep an eye out for it then. Okay. Hey, what do you get? 0.323 units? None. Now, I said minimum coefficient of friction in the question because if it was exactly that, you would be very uncomfortable because you would feel like you were just about to slip. I'm willing to bet they probably have a... Do they have a fabric or something behind you when you're in it on your back? Yeah. I'm willing to bet it's a fairly rough fabric. I would guess probably has a coefficient of friction of like 0.5 or 0.6, a good safety margin, I suspect. Anyways, that's the physics of that ride. Or if you were designing the ride, you would do this whole operation in reverse because you would know what fabric you had, you'd know your coefficient of friction, and you'd say, what kind of motor do I need? How fast do I need to have it rotate for it to be safe? So another way would be to reverse this question and say, hey, find the minimum period of safety. But you start out with the same free body diagram and you just cross multiply differently at the end. Example 7. A toy plane is attached to the ceiling with a string. It has a little propeller which causes it to move in a circle as seen below in side view. I'm hoping maybe you've seen these sometimes in a shopping mall or in stores. I bought 2 and each of them hasn't worked, so I need to do some internet research and read some reviews and find one that does work. What we're talking about is this. Hello, where'd I put you? My 3 red balls on a string? Ah, right there, screen line. We're talking about instead this shape, but what's causing it to rotate is this little toy plane that has a propeller that's pushing it that way, or pushing it this way. And that's enough to just keep it going in what we call a conical pendulum. Conical because it's shaped like an upside-down ice cream cone. See it? The path I'm tracing it? It's called a conical pendulum. This is nice because the circle is still horizontal, but the forces are not. Ooh, let's bring in some vectors. It says this: if we ignore air resistance and the force from the propeller, which balance each other anyways, so once it achieves equilibrium, the propeller is pushing it in a circle, air resistance is exactly matching the acceleration of the propeller, which means it's going at a steady speed. We called that uniform circular motion. So if we ignore those two, which of the following is the best force diagram for the plane? What do you think? Let's see if we can reason this out. What are the forces acting on this airplane? Get the obvious one. What else? Tension? What else? Nothing. No, Mr. Dewick, you said that if you're moving in a circle, and I can see there's a little picture of a circle there, Mr. Dewick. You said if you're moving in a circle, there has to be a net force pointing inwards. There is. No, man, watch. If I take these two, only these two, if I take these two forces and their vectors, how could I add them together? The vector diagram looks like this. There's gravity. There's tension. What's the resultant? There's circular force, which does not appear on my free body diagram. The correct free body diagram is C. Those are the only two forces you need to move it in a circle. Oh, and Terry, because I know the circle is horizontal, which means I know that my resultant has to be pointing towards the center, I knew that I wasn't going to draw tension that long, because that would give me a resultant like, no, I know it's not that. And I knew I wasn't going to draw tension that long, because that would give me, you know what? If it's a horizontal circle, it also intuitively told me, draw, 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 stop. That's what's going on when you play tetherball, or when you spin something on it. I'm assuming at least once in your life you spun something on a string around your head. Those are the two forces, gravity down, tension. And when you add those two forces together vectorially, you get a net force towards the center. So in a horizontal, I explain why the others are wrong, we just did. In horizontal circles, your vertical forces are balanced, and there is a net or an inwards force, which is ma, which is either mv squared over r or m4 pi squared r over t squared. And your speeding up and slowing down forces are balanced as well because you're going at a constant speed. We called that uniform circular motion. Let's look at a few more weird examples. Example 8. Let's look at this conical pendulum. It's kind of a nice one. It's a nice chance to do some vector math. It says redraw the force diagram. Okay, it was gravity down, tension at an angle. But again, does FC appear on my free body? Nope. Will it in my calculation? Yeah. And then it says write the force equations. Let's add these together tip to tail. If I was drawing this, which of those two vectors is the easiest one to draw? Tension or gravity? Gravity. Always draw the easiest one first, if you can, if you have a choice. Because it's going to look like this. Gravity down, and once I have that reference, I know draw, 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 stop. Tension. Here's FC. Now, I notice that when the tension arrow meets a vertical line, that's angle theta from my diagram, which means I think that's angle theta from my diagram, which means I can use my Z angles, and I'm pretty sure, Gabby, that's angle theta. In fact, I'm positive that's angle theta right there. Now that I have that, I can come up with a couple of equations. Which trig function relates circular and gravity? Dorothy, you're right. You're right. Yeah. One of the equations that comes out of here is tan theta, which ends up being opposite over adjacent. This is the physics, this is the equation behind, at Playland, the wave swinger. The swing sets with the music that you sit in and they swing you around it. And this is the physics of the atmosphere, which is the new one they just added last year that I haven't been on yet, that I'm totally looking forward to going on. Pardon me? You like drool if you try to talk?
Drool? You almost drool. Yeah, your skin goes like that.
How many of you been on the Revelation at Playland? That's the two big spokes with the basically the swing sets on either end that go in the huge circle. Okay, we get when we go on the Playland field trip, I get one free Revelation ticket. I always give it to the top Physics 12 student, unless they don't want it, then it goes to the second or whoever. But we analyze that one. That's a fun one to crunch, specifically the tangent velocity that you're traveling at. The tangent velocity that you're traveling at is staggeringly high. You're road legal and then some in that little swing set when you actually crunch the numbers. We'll talk about that in May. Oh, and by the way, what's the equation for FC? MAC over MG, yes? Did you go on the atmosphere, Megan? Did you have to step on a scale before you went on the atmosphere? Why? Now, how many have you been on the wave swing or one of those swing rides? How many have been on one of those? Next time you're on it, check out the empty seats. The empty seats do not swing out higher. They don't swing in lower. They also stay in line with you. Why? This is cancel. That's if you know mg. Maybe you don't know mg. Maybe you only know tension. What equation, what trig function would relate tension and centripetal force? Which trig function relates those two? Time. Here the masses don't cancel. Oh, that does make sense because if something is too heavy, it could snap the rope. Okay. There the mass shouldn't cancel. Example 9. The picture below shows a frictionless tabletop in top view. The mass is 4.15 kilograms. It's attached to a 2-meter long string, and it's moving at 2.5 meters per second. Write force equations and solve for the string tension. So we're talking about this. Look back here for a second. Just watch. I think the situation I'm talking about is you're spinning a mass around in a circle like that. Okay? I don't know what's spinning it around. The question doesn't say. Maybe there's a little motor in the middle. I don't know. But, okay. There's my top view. What are the forces acting on this mass? Get the obvious ones. I guess gravity would be straight into the page. Normal force would be straight out of the page. Those are awkward to draw, so I'm just going to make a little note over here. But I'm not going to, I don't know how to draw it into the page and out of the page. I don't know how to do that like 3D-ish. But here's what I can tell you. What path is this shape tracing out? So where must my net force be? Toward the So there has to be a force toward the center. Which force? I think it's tension. In fact, I think it's tension equals Fc. So there's my force equation. That's the first thing they asked me to do. And solve for the string tension. Oh, I guess this is going to be MAC. Which circular acceleration am I going to use here? Well, let's look at what they gave me. Which one am I going to use here? I think v squared over r, because they gave me a v. So it's going to be 4.15, 2.5 squared, all over 2. How much tension is there in this piece of string? Yeah, I told you, right? How much tension is it? What's the tension? 15 point? 13.0? 13.0 even? Wasn't it like 12.98 or 96? Yeah, okay, I remember this one now. Units? Newtons. Hey, what if I spun this twice as fast? What would happen to the tension? 4 times bigger. In fact, in theory, you could spin this so fast that the string would snap, which happens sometimes in real life. Example 10. Here's our conical pendulum again. Tetherball. A blue ball is swung around in a horizontal circle, and it completes a single rotation in 1.2 seconds. Got it. The 0.44 meter long cord makes an angle of 35 degrees with the vertical during the ball's motion as shown. For some reason, letter A didn't show up. A, what's the centripetal acceleration of the ball? Okay. Let's do that right here. Which equation do you think I'm going to use for centripetal acceleration? Which one am I going to use for AC? I got 2. Which one? 4 pi squared. Oh, yeah, they give me the period. Okay. 4 pi squared r over t squared. Now, John, they gave me the period. Great. What didn't they give me? Didn't give me the radius. Well, in the picture, they said this has a length of 0.44. They said that this has an angle of 35 degrees. That's the radius right there. I think I can find the radius using like grade 9 trig. I think it's going to be opposite over hypotenuse. I heard somebody say tan. Actually, this is a sine. We're so used to it. It's almost always been tan. This time it's sine because it's the hypotenuse. Okay. In fact, I think we can say sine 35 equals r over 0.44. Yeah? How would I get the r by itself? Sorry? You know what? Let's just plug that straight in over here then. So I think it's going to be 4 pi squared. For r, I'm going to write 0.44 sine 35, all divided by, what was t? What was 1.2 squared? Okay. What's my circular acceleration? Back in a second. What'd you get? 6.92. Anybody else? Go. No? Yeah? 6.92 in acceleration, meters per second squared. B says, what's the centripetal velocity? I'm going to need more room, I think. Let's do B down here. Now, this is the equation that is not on your formula sheet. You have to realize that velocity is distance over time. It's meters per second. But when we're talking about a circle's distance is the circumference, 2 pi r. Now, I think the equation for the circumference of a circle is on your formula sheet, divided by, what's the time to go once around? What do we call that? Period. This is the equation for circular or centripetal velocity. It's 2 pi r over the period. Not on your formula sheet. You've got to derive it. But I think I just showed you how to. It's going to be 2 times pi times, what was r? R was 0.44 sine 35. Divided by the period 1.2. Do you get 1.32? Is that right? Meters per second. I added part C, but I'm going to skip part C, turns out. Strangely. Last one. This is a really tough one to visualize. It says a 9 times 10 to the negative 3 kilogram ball, a lighter ball, is attached to a heavier mass by a string which passes through a hole in a frictionless surface. The ball is traveling in a circular path of radius 0.42 meters. What's the speed of the ball? It's hard to visualize what's going on. Here's what we're talking about. Look up for a second. Okay? I want you to imagine that this ball, this one here, is on the table. I don't have a table, I don't have this apparatus set up. Normally, if I just let go and the bottom ball is heavier, it's going to go whoosh. Okay? However, watch what happens to the bottom ball if I start to spin this. Watch. Did you notice the bottom ball started to go which way? Up. If I have a heavier ball here and a lighter ball here, I can achieve an equilibrium. I can achieve where all my forces are imbalanced. That's what they're talking about here. Okay? Too much work to try and set that apparatus up. And I have a table with a hole in it, and it's frictionless. Anyways, that's what we're getting at. So, they want me to find the speed of the ball. I think I'm going to start out by labeling my forces. Let's do the bottom mass. What are the forces acting on that bottom mass? Get the obvious ones. I'll call that big M G. What else? You're right. What was it? Tension. And I think that's it for that guy. It's vertical, it's not moving in a circle. The top ball, what are the forces acting on it? Well, we'll have little mg and a normal force. It's a frictionless surface, so no friction. What else? You're right. There has to be a force that way. Which force is that? Tension. In fact, I think what we're saying is this. Tension equals Fc. Tension is what's pulling this ball in a circle. I think what we're saying is this. Tension equals little m. Which equation do I want to use? The 4 pi squared r over t squared or the v squared over r? Why do I want to use v squared over r? Oh, they say it's find the speed. Okay. Do I know little m? Yeah. Do I know the radius? 0.42. Yeah. Do I know tension? Oh, wait. There is a second equation I can get out of here. That bottom mass, is it in balance? Is it in equilibrium according to this question? Then I think I can also say those two are the same. They must be. Which means I think I can take this. I think I can modify my equation to become big M G equals little m V squared over R. I think I can rewrite this and get the V by itself. It's going to be big M, GR, divided by little m, and that's V squared, so I think I'm going to square root. Big M was 3.6 times 10 to the negative. You know what that is? That's 0.036, which I think is less writing. G is 9.8. What was the radius? I've scrolled down. 0.42. All divided by little m was 9 times 10 to the negative. You know what? That's 0.009. Also less writing. So a 36-gram weight is the big mass, and a 9-gram weight is the small mass. If you want to have these stay steady, if you want to have these in equilibrium, how fast does that small mass need to be moving? I'm getting 4.06, am I not? Yeah? 4.06 meters per second. So lots of stuff we can do if we combine horizontal circles, what we know about centripetal force, and a good free body diagram. Can analyze outer space and amusement parks, which is way cool. What's your homework? Now this is due for Wednesday because Monday you've got a test. Your homework for Monday is finish the bonus video game if you haven't already, if you want to, and finish the big unit review. But for Wednesday, I think you can do number 1, number 2, number 3, skipping 4, number 5, skipping 6, number 7, eight, 9, 10, and 11, and 13. Seems like a lot of these are just conceptual, think about it, and some of these I already talked about in class. It's just to reinforce what I talked about in class. Got a couple of videos, cool ones to show you.